All right, today let's take a look at two more types of free response questions. First, we will look at graph and function analysis, which is basically, here's a graph of the derivative, give me information about the original function. So you are not expected to write the original equation. You're just expected to determine important features. Generally, that means where the original function is increasing, decreasing, concave up, concave down, mins, maxes, that kind of stuff. Right? So what you should be able to do, read information about the original function from the graph of the derivative. This can be approached by derivative techniques or antiderivative techniques. Find and justify where the original function is increasing or decreasing. Okay, that's wherever the derivative is positive and where the derivative is negative. Find and justify extreme values, meaning mins and maxes. Okay, a min would occur where the derivative changes from negative to positive, and a max would occur where the derivative changes from positive to negative. Points of inflection. Points of inflection would occur where the slope of the derivative changes sign. Right? So where the graph of the derivative changes from increasing to decreasing or decreasing to increasing. Find slopes from the graph. Write an equation of a tangent line. This is a common piece that can show up on questions of this type. Riemann sums can show up on this type of equation as well. Evaluate an integral from the areas on the graph. Okay, we may have to use, area of a trapezoid or triangle or semicircle, those types of things to find area under a curve. And we also looked at problems where functions were defined as the integral of some given graph, which is the same type of problem. Right? It's just saying, here's a graph of f, g is the antiderivative or the integral of f. Okay, so we need to understand from those that the derivative of g, okay, if we're given an integral problem, is equal to the graph. And we'll look at a full problem like that. Here's our first example. Now, one big thing is we need to make sure that we write that in our answer somewhere. Okay, and I'll show you what I mean here on the first problem. All right, so let's go ahead and jump into this first example. So here we're given a graph of f and it's defined between -4 and 12. And we're saying that g is the integral of f from 2 to x. So part A just asks, does g, the original function, have a relative minimum, a relative maximum, or neither at x equals 10? Okay, so to figure out mins, maxes, or neither, right, we're just kind of thinking about a sign chart. Right? So if I make a sign chart here of f, okay, and this is the same thing as g prime, the derivative of g is equal to f. The places where f equals 0 are -2, 2, 6, and 10. Right? So then we're saying, well, the derivative is negative here, positive here, positive here, negative here, and negative here. So at 10, we don't change sign. Therefore, the original function, g, has neither a min or a max. So we need to write out that answer and justify. Remember, whenever it says justify, we need to write out like a sentence. So we can say g has neither a min or max because g prime, I guess we should say, of x. So here's what I was talking about in the last bullet point in the last problem. Okay, we need to state that we understand that the derivative of g is the same as f. So we can say that g of x has neither a min or a max at x equals 10 because g prime, which is equal to f of x, does not change sign, right? It stays negative. Therefore, there is no min or max, all right? Next part, part B, says, does the graph have a point of inflection at x equals 4? Okay, well, points of inflection, we think about second derivative. So if I make a second derivative sign chart here, remember that's wherever the slope changes sign. So that would occur at 0, at 2, at 4, at 8, and at 10. Right? So here the slope is positive, then negative, then positive, then negative, then positive. So at x equals 4, the slope of f does change sign. Therefore, g would have a point of inflection. So to write out our explanation, because again it says justify your answer, we can say g of x does have a point of inflection at x equals 4 because, I guess I actually labeled this wrong, didn't I? I should have labeled this as g double prime, which is the same as f prime. Okay, so g of x does have a point of inflection at x equals 4 because g double prime of x, which is the same as f prime of x, changes sign at x equals 4. All right. Part C then says find the absolute minimum and absolute maximum values on the interval. Okay, well, absolute mins and maxes could occur at critical points or at end points. Right? So if we're thinking about critical points, let's go back to that sign chart we made here. So for f, we said, well, we change sign at -2 and 6. Right? We were already able to say that we know that 2 and 10 are not critical points because the sign of f does not change. So here we are negative, then positive, then negative. Right? So my critical points are -2 and 6, and then my end points are -4 and 12. So I want to evaluate all of those things. I want to evaluate g of -4, g of -2, g of 6, and g of 12, right? Absolute mins and maxes can occur at critical points or at end points. So I need to evaluate all 4 of these things. Now what that means is I'm plugging all 4 of these values into this integral. So this first g of -4 means I want the area from 2 to -4 of my graph of f of t dt. Okay, so it might be a good idea to just find all of these areas here before we get started evaluating these. So here we've got a triangle with a base of 2, a height of 4, so 1/2 times 2 times 4 would be 4. Here, base of 4, height of 4, so 1/2 times, excuse me, 1/2 times 4 times 4 would be 8. Same thing here, 4 and 4 times 1/2 is 8. 4 and 4 times 1/2 is 8. And here this would be 4. So if I'm starting at 2 and going to -4, remember we're going backwards. So this would actually be the same as the opposite of the area from -4 to 2. So we can say this is -4 plus 8. So this would be 4, but it will be -4 since we have that extra negative sign. Okay, so now we don't have to write all of this out to show our work. All right, I just wrote it all out to kind of explain what we're doing. Then g of -2, okay, again, we would be going backwards because this would be the integral from 2 to -2 of f of t dt. So that would just be going backwards, so that would be -8. G of 6 would be the area under the curve from 2 to 6, so that would be +8. And then the area from 2 to 12 would be 8 minus 4, so that would be -4. So to answer the question then, okay, the absolute minimum occurs at -2, and the absolute minimum value is -8. The absolute maximum occurs at x equals 6, and the absolute maximum is 8. Right? So we need to write that out in a sentence. Okay, we could say the absolute, if I could spell, absolute max is 8. At x equals -2, and the absolute min is -8 at x equals -2. All right. Then the very last part, part D, just says find all intervals for which g is negative. So here we're just kind of interpreting what's going on here. So if I am starting at this value and I go to the right, I would start accumulating positive area. Okay, and we said that, if we remember, these values were 8, 8, 4, 8, and 4, right? So if I start here, I accumulate positive area until I get to here. Then I accumulate negative area to here, which actually 8 and -8 cancel out. So right here, I'm at a total area of 0. Okay, g of 10 would be 0. But then I accumulate more negative area. So only from 10 to 12, if I'm thinking about going in the positive direction, is g negative. So let's say x is between 10 and 12. Then, if we think about going in the opposite direction, remember, if I'm going backwards, this up here is actually negative area. So I would be accumulating negative area all the way to here. So this would actually be -8. And then down here, this would be accumulating positive area. But my net accumulation would still be negative. If I'm at -8 here and I add 4, I would still be at -4 total area here. So this entire area, or this entire interval, g is negative. So we would also say from -4 up to 2. Right? So that's the entire first question here. If we look at our scoring rubric, part A was only worth 1 point, okay, saying that it was neither a min or a max. Part B was only worth 1 point, saying that yes, there is a point of inflection there. Part C was actually worth 4 points, okay, and if you look at the breakdown, okay, 1 point for considering the critical points, and then another point for considering the endpoints, and then 2 points for the answers, okay, finding that -8 is the absolute min and +8 is the absolute max. And then part D was worth 2 points for the correct intervals. Now, interesting, up here, you got 1 point just for stating somewhere in your entire answer that G prime is equal to F. Okay, and we said that in part A. If we look back at part A, we just, here in our explanation, we said g of x has neither a min or a max at x equals 10 because g prime, which is equal to f of x, does not change sign. Okay, so on a problem like this, you got a point just for stating that somewhere in your answer. All right, let's take a look at the next one. So on this one, we've got a function that's differentiable in a closed interval, and we're given an initial condition. Right? So we're told this is the graph of the derivative, and we're given 1 point on the original curve. The graph of f prime, the derivative, consists of 3 line segments and a semicircle. So on this one, we need to first, for part A, evaluate f of -6 and f of 5. So here is where we want to use the fundamental theorem of calculus. So first, if I want to evaluate f of -6, I'm going to use -2 and -6 as my x values. So I can say the integral from -6 to -2 of f prime of t dt or x dx, doesn't really matter, is equal to f of -2 minus f of -6. So I know f of -2 is 7, and then I can evaluate this integral from my graph. So all that ends up being is this triangle, right, from -6 up to -2. So I've got a triangle with a base of 4 and a height of 2, so 1/2 times 2 times 4 would be 4. So this is just equal to 4. So we've got 4 equals f of -2 is 7 minus f of -6. Subtract the 7 over, and then divide by -1, and we get that f of, -6, we get f of -6 is equal to 3. Right. Similar idea for f of 5. Again, my two x values would be -2 and 5. So here, if I want to put these in order, it's easier if we put the bounds in order. Smallest one on the bottom, greatest one on the top. So I can say of f prime of t dt is equal to f of 5 minus f of -2. So here, the area from -2 all the way to 5. Okay, well, this is going to be this semicircle and this triangle. So this semicircle would be 1/2 times pi times the radius of 2 squared. Okay, but if I'm starting at -2 and going this way, this area will be negative. So this will be a negative area. And now this triangle, we've got a base of 1, 2, 3 and a height of 2. So 1/2 times 3 times 2 would be 3 equals f of 5, which we're solving for, minus f of -2, which is 7. So here, this is 4 times 1/2 would be 2, so -2 pi plus 3 equals f of 5 minus 7. Add the 7 over. So we would have -2 pi plus 10 equals f of 5. All right, so those are our two answers for part A. Part B then, on what intervals is the original function increasing? Justify your answer. Okay, well, wherever the derivative is positive is where the original function is increasing. So we can think about that in terms of a sign chart. My zeros would be -2, +2, and then my endpoint of 5. So the actual value of the derivative is positive, then negative, and then positive. So the intervals where this function is increasing would be -6 to -2 and 2 to 5. So we can say f of x is increasing on -6 to -2 and 2 to 5 because f prime of x is positive on these intervals. Okay, remember, whenever it says justify, you have to write out a short explanation like that. All right. Now, part C says find the absolute minimum value of our function on the closed interval. So, we know that absolute mins could occur at endpoints or at critical points. Right? We just said that our critical points are -2 and +2, and then our endpoints are -6 and 5. So what we want to try to figure out here is f of -6, f of -2, f of 2, and f of 5. Right? Our two critical points and our endpoints, whenever we're finding absolute mins or maxims. So we already have found some of these values. Right? We already found that f of -6 was equal to 3. We found that in part 1 here. F of -6 is 3. We found that f of 5 is -2 pi plus 10. We're given that f of -2 is 7. So we just need to find f of 2. So come off to the side here. If we use our initial condition, we'd be going from -2 to 2 of f of t dt. So that would be, whoops, of f prime of t dt. So that would be f of 2 minus f of -2. So this would just be the area of this semicircle, okay, which would be, we already found would be 2 pi, but it's beneath the x-axis, so that'll be -2 pi equals f of 2 minus f of -2 we know is 7. So add the 7 over, we get -2 pi plus 7. So -2 pi plus 7. So we want the absolute min. We need to figure out which of these values is the smallest. Okay, well, obviously, -2 pi plus 7 is going to be smaller than -2 pi plus 10, because we're adding a larger value here. But then we need to figure out what is this equal to. Okay, well, if we know that pi is 3.14, 2 pi would be 6.28. So 7 and -6.28, that's going to be less than 1. Right? So what we end up with is this is the minimum value. Okay, so showing our work and justifying our answer. Okay, again, remember it says justify, so we would want to say that the absolute minimum value is -2 pi plus 7. This occurs at x equals 2. And then our work here, okay, testing each of these points, can be our justification. All right? The final part for this question says find f double prime of -5 and f double prime of 3. Okay, well, the second derivative of the original function is the first derivative of the first derivative. What that means is f double prime will just be the slope of this graph. So the slope at -5, okay, right here. I want to find the slope of this piece. Well, this is just a line, right? So f double prime of -5 is just the slope of this line. So I'm going, let's see, rise over run, I'm going down 2 and right 4. So -2 over 4 is -1/2. Then the slope at 3, well, right here, slope at 3 doesn't exist, right? Because we have a corner there. So we can say f prime of 3 dne, because we could write this out a bunch of different ways, but I'm going to say f prime of x is not differentiable at x equals 3. Therefore, the second derivative wouldn't exist. All right? So these types of problems will show up on the AP test. Okay? There have been estimates that about 15% of the points on the AP test are problems like this, graph interpretation like this. So make sure that you are comfortable with problems like this. All right. So here's the scoring rubric. Okay, we can see that part 3 was worth 3 points. Okay, 1 point just for using the initial condition, and then another point for each of the correct answers. B was worth 2 points, showing our intervals. Part C was actually only worth 2 points, okay, considering our 4 values and then our answer that the absolute min occurs at f of 2. And then D was worth 2 points, finding that f double prime of -5 is -1/2, and finding that f double prime of 3 does not exist. All right, next type of free response question, area and volume. Okay, this is the one that we've done most recently. So hopefully these are fresh in your mind. What you need to be able to do for these are find intersections of graphs and use them as our limits of integration. So a lot of times these are calculator problems where we can just graph these and find the points of intersection. Then we need to be able to find the area of a region between graphs, find the volume when the region is revolved about a line. Okay, it could be an axis, or it could be any other horizontal or vertical line. We need to be able to find the volume of a solid with given cross sections, like a square, a rectangle, a triangle, a semicircle, those types of things. And then we've only done a couple of problems like this, okay, but this has become a more popular topic recently. Find the equation of a vertical line that divides the region in half. Okay, so that's the type of thing where we said, well, if we have the entire region, we're going to say we want the area from 0 to k of our function to equal the area from k to the end of our function, right? Setting up some integral like that where we want the areas to be equal, and we're saying we're stopping at the same point that we're starting for our other integral. All right, so let's take a look at a few examples. Okay, this first example was on the calculator portion. All right, so we're given two equations, 1 minus x cubed and sine of x squared. And first, we just want to find the area of R. So to find the area, we need first our limits, right? We know that we're going to be setting up an integral like this. Okay, and we know that we're going to be starting at 0. Okay, my x value would be 0, but then I need to find this point of intersection here. Well, to do that, I can graph these two functions on the calculator and use Calc 5 to find a point of intersection. Okay, I'm not going to do that for time's sake in this video, but please, please, please tell me if you don't feel comfortable doing that on the calculator, and I can show you how to do it. Right? But if we do that, that value ends up being 0.764972. So that'll be my upper limit of integration here, 0.764972. Now, I will just have the top function minus the bottom function, and they give us that in the picture. The top function would be 1 minus x cubed, So I will have 1 minus x cubed minus my bottom function, sine of x squared, dx. Make sure you're using parentheses appropriately here, putting parentheses around the first function, then minus, you could even put another set of parentheses around sine here. Now, this was a calculator question, so I can just plug this into the calculator, and I think we get 0.533 or 0.534. Okay, remember they'll accept either rounding or truncating. Part B then says a horizontal line, y equals k, is drawn through the point where the graphs intersect. So that's saying I'm drawing a horizontal line right through here. I want to find k and determine whether this line divides R into two regions of equal area. Show the work that leads to your conclusion. Okay, well, we found this point of intersection. We knew that this x value was 0.764972, and when we find that point of intersection, it'll also give us the y value. So we would get that the y value is 0.552352. So right off the bat, we can say that k is equal to that, 0.552352. Now, I want to determine whether this line divides R into two regions of equal area. So I need to find the areas of these two regions separately. So the first area would be top curve minus bottom curve, 1 minus x cubed minus this number. So that'll be my first function. So 1 minus x cubed. I don't know why I'm writing so small. Let me write this a little bigger. 1 minus x cubed minus 0.552352. All right, so that'll be the area of this piece right here. And then my limits of integration will still be 0 to 0.7649772. So put this in the calculator, and we get 0.257. Then we want to find the area of this region. Okay, well, this again will be top curve minus bottom curve. So in this case, it'll be 0.552352 minus sine of x squared. So 0.552352 minus sine of x squared dx, and again, limits of integration will still be the same. So putting this into the calculator, we get about 0.277. Okay, so to actually answer the question, determine whether this line divides R into two regions of equal area, we would want to write this out, write our answer. No. K does not, or y equals k, does not divide R into equal regions. Okay. Part C then says find the volume of the solid generated when R is revolved about the line y equals -3. Okay, y equals -3 would be some line down here, right? So here we have to think about big R, little r. Right? Little r would be the distance from my axis of revolution up to here. Big R would be my distance from the axis of revolution to my top curve. So if I write out my entire, I'll do it up here, my a of x is pi times big R squared. So pi times that distance would be 1 minus x cubed minus negative 3. Okay, so 1 minus x cubed minus negative 3 would just be the same as plus 3, right, squared. So pi times big R squared minus pi times little r. So little r is sine of x squared minus negative 3. Sine of x, sine of x squared minus negative 3 squared. So to get the volume, I would just integrate this function. I can pull my pi out. I know that my bounds are still going to be the same, 0 to 0.764,972. And then we've got, again, making sure we're using correct parentheses, squared minus sine of x squared plus 3 squared dx. So plug all of that into the calculator and we get about 11.841. Okay, make sure that you are comfortable plugging things like this into the calculator. All right. So I mean, even just pause the video and double check. All right, plug all this in the calculator and make sure that this is what you get out. All right, so that's our first example here. Here's our scoring rubric. Okay, you can see that this is similar to one of the ones we just looked at, where 1 point for correct limits in any part, A, B, or C. So I mean, maybe we messed up the limits somewhere else and we accidentally used a different point. Okay, we would get a point for using the correct limits somewhere, right, from 0 to 0.764972. Part A was worth 2 points, 1 point for the integrand, 1 point for the answer. B was worth 3 points. Okay, 1 point for the integrals, 1 point for the values of the integrals, and then 1 point for saying no, they aren't the same. And then part C was also worth 3 points, 1 point or 2 points for the correct setup, and 1 point for the answer. All right, one more. In this example, it says let R be the region in the first quadrant enclosed by the graph of f of x equals the square root of cosine of x, the graph of e to the x, and the vertical line x equals pi over 2. All right, so first, write but do not evaluate an integral expression that gives the area of R. So we should be able to tell that this is e to the x. This would be the square root of cosine, this function down here. If you're not 100% sure on that, you could just plug 1 in, okay, and we would get e, if we plug 1 in to g, and then cosine of 1 is some, we know it's in between -1 and 1, and then the square root of that would definitely be less than e. So e of x will be my top curve, square root of cosine of x will be my bottom curve. My bounds, we're actually given those, would just be 0 and pi over 2. So to set this up, we would just say this is the integral from 0 to pi over 2 of e to the x minus the square root of cosine of x times dx. Okay, and remember, when you're writing this out, we have to show that everything is being multiplied by dx, so make sure that you're using parentheses around what's being integrated. Okay, and that's it. That's all of part A. Write but do not evaluate an integral expression that gives the area of R. Part B, find the volume when this solid is revolved about the x-axis. So here, if I'm revolving about the x-axis, I'm going to have to think about big R and little r. So this would be my little r. This would be my big R. So my area function would be pi times little r squared. So little r would just be the square root of cosine of x minus 0. So this will be the square root of cosine of x squared. Whoops, I did that backwards, didn't I? Pi times big R squared comes first. So pi times e to the x squared minus pi times the square root of cosine of x squared. Which we can simplify this a decent amount, right, and say this is pi times e to the 2x, right? I can multiply exponents together, minus pi times just cosine of x. So now, to get the volume, I will integrate this. So this will be the integral. I can pull my pi out. Integral from 0 to pi over 2 of e to the 2x minus cosine of x dx. Now, this is actually, or was actually, a non-calculator problem. So we would have to do these antiderivatives by hand. Okay, they're not bad to do by hand. If I want the antiderivative of e to the 2x, technically we would want to think about that as a u substitution problem. So I'm going to come over here and go ahead and do that. We would have u equals 2x, du equals 2 dx, but I just want my coefficient to be 1, so I would need to multiply by 1/2 times 1/2, so we get 1/2 du equals 1 dx. So what that means is we would have 1/2 times the integral of e to the u du, so that'll be 1/2 e to the u, which is 1/2 e to the 2x. Now, if you can recognize that without doing this much work, that's perfectly fine. Okay? If you can recognize, well, I would just need to multiply this by 1/2 because I would have an extra 2 out there. Perfectly fine. Okay, so the antiderivative of this piece is 1/2 e to the 2x. Antiderivative of negative cosine would be negative sine. And I want to evaluate all of this from 0 to pi over 2. So I'm going to plug in pi over 2 first. So pi times 1/2 e to the 2 times pi over 2 would just be pi minus sine of pi over 2 minus, now we have to plug in 0, so we still have that pi out front, so pi times 1/2 times e to the 0 minus sine of 0. Now, we do actually have to evaluate these trig functions, but I can leave everything else as is. Right? I can leave that pi, say this is 1/2 e to the pi. Sine of pi over 2 is equal to 1 minus pi times 1/2. E to the 0 is just 1, so 1/2 times 1 is 1. And then sine of 0 is 0. So that's our answer. We can just leave it like that. We do not have to simplify from there. Once we have all numerical values, we are done. All right. Then part C says that region R is the base of a solid whose cross-sections perpendicular to the x-axis are semicircles with diameters in the xy plane. So what that's saying is, here's the diameter of my semicircle, and then coming out of the board are semicircles. Write, but do not evaluate, an integral that gives the volume. So what we're saying is, we've got a semicircle whose diameter is the distance between my two functions. So the diameter here is e to the x minus the square root of cosine. Well, the area of this semicircle, okay, remember our goal is always to write the area of our cross-section. area is pi times the radius squared. Well, the radius would be the diameter over 2, right? So e to the x minus the square root of cosine of x over 2 squared. So pi times the radius squared. So then the integral of that would be 0 to pi over 2. Whoops, I forgot my 1/2 out here, didn't I? Because this is half of a circle, so the area is 1/2 pi r squared. So we're integrating this function, 1/2 times pi times e to the x minus the square root of cosine of x over 2 squared dx. And we could pull this 1/2 pi out front, doesn't really matter. All right, and that's it. It says do not evaluate. So this would be my volume for this situation. Okay, so whenever we've got a known cross-section, whenever they tell us what the cross-sections are, we just have to write our area function. And we have to be careful. Okay, I almost messed that up by forgetting my 1/2 out here because this is only half of a circle, not a whole circle. All right, so I want you guys to go ahead and try the 2 practice problems. I will send out solutions to those later this evening at 5 o'clock. And please, please, please don't hesitate to send me questions. I love to answer questions. All right.